So I'm very happy to introduce our first speaker, Maru Sarazola, who's going to be speaking to us on a double categorical frameworks for algebraic K-theory. So please, Maru.
Yeah, thanks so much. I'm super excited to be speaking here today because usually when I give this talk, it's to a K-theory crowd, and I need to sell double categories to those people so hard. So I'm actually happy to be talking to folks who admit that they are beautiful and useful, kind of as a given. Um, but I thought that instead I should motivate K-theory a little bit for this crowd instead. So what I'm going to do is I'm going to give kind of a panoramic view of what we are trying to do when we do algebraic K-theory and kind of what frameworks are classically available to us when we do that. And then we will bring some squares into the story. So I want to start by saying something about how algebraic K-theory works. So what we typically have is we have some kind of categorical input that we care about. So these are the things that you want to study. And when you do K-theory, the first thing that you do is you run them through some kind of black box K-theory machinery. So that's this part over here. And your machinery is going to spit out something topological in flavor. So it will be either a topological space or a spectrum. And that's what we denote by K of C. And then we grab that space and we run it to another box, but this one is very familiar. That's just taking homotopy groups, and we produce a bunch of abelian groups, and that's what we call the K-theory groups. So what I want people to take away from this kind of diagram here is that the second part of the process is always the same. So once you construct somehow your K-theory space, you always take homotopy groups of it to produce the K-theory groups. However, the first part of the process heavily depends on what machinery you choose to put inside of this box. And it turns out that sometimes your hands are kind of tied on what you can do, but sometimes you have some leeway for determining exactly which K-theory machinery is going to be more convenient to your own purposes. So when I said, okay, we start with some input, but of course we can't do just algebraic K-theory of any given category. So what are some possible inputs that we may want to do algebraic K-theory of? And I want to mention two different flavors today. So the first one is the one that was actually kind of the birth of algebraic K-theory, is when you have some kind of algebraic structure. And when I say this, so formally I really mean you have an abelian category, or if you like, you have an exact category. But if you're not super familiar with these terms, you can just think you have a category of R modules for your favorite ring, and all of the intuition is going to work perfectly fine. So if you have one of these algebraic structures, what are the important features that I want to highlight? So I'm not going to give you a definition of what these categories are, but what do they have that are going to matter for K-theory? Well, all of these have a zero object, and they have a notion of monomorphisms. So they have monos and epis that are pretty well behaved. So in particular, we're allowed to take kernels and co-kernels of these monos and epis, and they're going to induce short exact sequences. So what do I mean by this? Let's say that we start with a mono from A to B. So I'm going to denote the fact that this is a mono by putting a zero over here. Then in one of these algebraic structures, I'm allowed to take the co-kernel. This exists. It's the equalizer of this map and the zero map. And it completes my mono to a short exact sequence. And similarly, if I start with an epi instead, I can take its kernel, and this always exists, and completes it to a short exact sequence. So this is a pretty important feature. And now if I give my K-theory machinery one of these guys, then what does K-theory do? Well, what it's going to try and do is it's going to try to split. So it splits these short exact sequences. That's kind of its ultimate goal. So what do I mean by this? We said up here that my K-theory is going to give me a bunch of abelian groups. So I'm going to describe the 0th group for you, because it's literally the only one that we can describe by hand. So K0 of one of these inputs is always going to be the free abelian group generated by the objects of my category C. And now I'm going to mod out by a bunch of relations. And these relations are going to tell me that whenever I have a short exact sequence, then I'm going to impose the relation that the middle term is the sum of the other two terms. So this is what I mean when I say that K-theory splits short exact sequences, because in particular, it's giving me the relation that the class of the direct sum of A plus B is equal to A plus B. And that's because I can always construct the split short exact sequence, which is just the trivial extension. So what we're doing here is not only are we splitting direct sums by using the trivial extension, but we're actually splitting any possible extensions. So that's what I mean when I say that it splits short exact sequences. So of course, this is just the 0th group in an infinite sequence of groups. So what's happening to all this higher information? How are we constructing that? Well, the question is now, how do we get a space? So how do we get a space from this algebraic data? Well, what you do is you take your category C and you apply to C what's called the Q construction. So this is going to give you a new category, Q of C, whose objects are the original objects that you start with, but now your maps from A to B are going to be spans. So you're going to take spans from A to B, you put any guy C up here, and the restriction is that this leg of the span has to be an epi, and this leg has to be a mono, and that's kind of how you're reflecting your algebraic structure in your morphisms. Of course, to make this work correctly, I should be saying iso classes of spans, and that's what really turns this into a category. And we compose, as usual, by taking pullbacks. So if I have one span over here, another span over here, how do I compose? It turns out that my properties of the abelian category allow me to take a pullback in such a way that this guy is an epi and this guy is a mono. So I can just take the outer span as we usually do, and that will be my composite. Okay, so now I've constructed this seemingly random category out of C. And now we get the space as follows. So I have my category QC. I'm going to take the nerve. So now I have a simplicial set. I'm going to take the geometric realization. So now I have a space. And we wish that this was the K-theory space, but unfortunately, we're still one step away. When you get to this space, you need to take loops on that. And loops on the space is your K-theory space. So hopefully at this point, you will believe me that this is pretty damn hard. Understanding this space and trying to compute any of its homotopy groups is a highly non-trivial pursuit. And that's why we have very, very few computations in algebraic K-theory that are thoroughly carried out. Okay, so basically what we're trying to do is we're trying to play the usual game that we have in homotopy theory, where we create a space whose connected components record some basic information. In this case, we're remembering which objects I'm allowed to split. But then we have all the higher homotopical information in this space that's recording not just which things split, but how they split and how these splittings are related to each other. So this is kind of the way that we need to think of these higher K-theory groups. All right. So that was for my first kind of input, the algebraic ones. I want to mention a second kind of classical input, which are homotopical structures. So formally, what I mean when I say this is I mean Wallhausen categories. But these are not super well known outside of K-theory. So if you've never heard of these, you should be thinking either a model structure where all objects are cofibrant, or if you want a really concrete example to get your hands on, you can just think chain complexes of our modules with quasi-isos. So both of these are good examples for the kind of properties that I'm going to mention right now. Okay, so now we are not necessarily in an algebraic world, but we do have something that looks like it. So what are the features for these kinds of inputs? Well, they also have a zero object. We have that both in chain complexes and in any general model structure. And now we have a class of cofibrations that are going to act like the monos did before. And these cofibrations, so before the monos gave rise to short exact sequences, now the cofibrations are going to give rise to what we call cofiber sequences. And really all I mean by this is that whenever I have a cofibration, I can take the unique map to my zero object, and one of my axioms in these structures says that the pushout exists. So I can take the pushout of this, and this thing is a cofiber sequence, and it's playing the role of the short exact sequences that the previous structures had. But now, of course, there's the homotopy bit that I haven't included yet, and that comes with a chosen class of weak equivalences. So what does K-theory do now? Well, it's going to try, so before, remember, K-theory tried to split the short exact sequences. Now it's going to try to split these cofiber sequences, but also it's going to glue along the weak equivalences. So that's how it takes into account this new homotopical information. So in particular, if I wanted to do the same K0 description, I would now get the free abelian group generated on the objects of my category. And now my relations are going to be that for any cofiber sequence, I ask that the class of the middle is the sum of the other two. But also that for any weak equivalence between two objects, those are going to represent the same class. Okay. So before, when we tried to construct the actual space to get the higher stuff, what we did was we did the spanny construction, and we can't really do that anymore because there's no axiom in this homotopical structure that ensures that we have pullbacks. And that was a key step that we needed to be able to compose. But it goes even beyond that. So let's say, okay, for some examples, that will be fine. For instance, in my chain complex examples, I will have pullbacks. But even if I'm able to do these spans, I'm not seeing the weak equivalences at all in any step of this process. So that should kind of clue us in that it's not the right thing to be doing. And so instead, for the higher homotopy groups, we construct a space in a very different way. So now we have two options. The first option is called the S-dot construction. So this is going to construct a simplicial category, and for the sake of notation, I'm going to tell you who n equals 3 produces. So for n equals 3, we're going to get a category whose objects are going to be a very special shape of diagrams. So I'm going to have my 0 objects, and now I'm going to have a chain A1, A2, A3 of cofibrations. But now I want to complete this with a choice of cofibers. So I can always take the map to my 0 objects, and we said one of the axioms tells me that the pushout exists. So I want to take a choice of pushout and that's going to be recorded as part of my object. So I'm going to take this A12. This is a push out, and it turns out that this is also a cofibration. Now, another axiom tells me that whenever I have a span and one of the legs is a cofibration, I can also take the push out. So cofibrations are going to be stable, in fact, under pushouts. So I can even complete this other one to an A13, and this is also a pushout, and that's how I record my first row of quotients. But now I have another cofibration here, which also has a quotient, and I want to record that as well. So I repeat the process once again. Take the map to 0, I take the pushout, and I record it. I take the map to 0, and now I'm done. There's nothing else for me to do. And this kind of staircase diagram is an object in my category S3. Okay, so my maps are almost what you expect them to be. So now we have like these diagram shapes as the objects. The maps are just going to be natural transformations with the condition, and that's what this W is doing over here, with the condition that these natural transformations are pointwise weak equivalences. And that's where I'm encoding my weak equivalences in this model. It's in the natural transformation direction. So now I have this simplicial category, WS.C, and you can think of a simplicial category as a bisimplicial set if you want. So we have this simplicial direction that makes the staircase grow bigger. It looks like a nerve direction in that sense. And then we have the depth direction that moves in the natural transformations with the weak equivalences. So if I realize this bisimplicial set however I want to, because they are all going to produce equivalent spaces, I realize this, and again I take loops, that gives me my K-theory space. So if the previous one was hard, this is even harder. This is much, much more complicated. All right, so that's one possible model. I want to introduce a second one, which kind of flies under the radar with K-theorists, but I think that this crowd is going to appreciate kind of the value in this construction. And it's called the Thomason construction. So here's another way to build your K-theory space. I'm going to build a very different simplicial category. And again, I'm going to tell you the 3. So this is the category whose objects are going to be sequences A0, A1, A2, A3 of cofibrations. So note that this kind of looks like the top row in my objects before, but I'm not imposing any conditions that I need to start with 0. So these are not encoding quite the same information. So these are going to be my objects. And now for the maps, let's say I have another A0 prime, A1 prime, A2 prime, A3 prime. My maps are just going to be commutative squares between these sequences with an additional condition, because so far I haven't encoded my weak equivalences. So those should appear somewhere. And the condition is going to be that if I take this push out, then the unique induced map I get to A1 has to be a weak equivalence. So these are kind of like homotopy pushouts in a way. And I ask the same for all of my squares. So if we stare at this for a little while, we'll see that what's kind of happening here is if I say, okay, I'm going to build a double category out of my homotopical structure, where I say horizontal morphisms are my cofibrations, vertical morphisms are any maps, and the squares are the ones with this push-out property. When I take the push-out, the induced map is a weak equivalence. Then all that this construction is doing is it's taking the horizontal nerve of that double category. That's really all that's happening here. So now I would define my space just as before. So I take the realization of this simplicial category, the realization of this horizontal nerve, and I'm forced to take these loops. to get the K-theory space. Okay. So this is kind of the classical picture, the kinds of inputs that you can have and the constructions that you have available for them. So now I want to make an observation, which is that if you squint a little bit, you can start to see double categories. So we already kind of mentioned how you can make a double category appear here, and this is the most natural one, but actually there's squares hidden in the background in all of the constructions that I just showed you. So for this one, it's not going to be the nerve of a double category, but still I could say, okay, I'm going to construct a double category, same with horizontal maps being cofibrations, vertical maps being any maps, and now I'm just going to take these squares, which have to be push-out squares, right? That was our condition here. So my squares are going to be push-outs. And now I can still do a pasting of my squares to define this simplicial structure. So I can still define it from the squares in a double category. And the previous one, the one with the spans, this is the one that's least obviously double categorically in flavor. However, bear with me for a second, because we said, okay, what's the important structure here? I have these monos and these epis, and how are they required to interact? Well, I need them to determine these short exact sequences. So each mono should give me an epi, each epi should give me a mono. And then I need to be able to compose spans by taking pullbacks. But all that I needed to do here was to be able to compose monos with monos and epis with epis. At no point was I required to compose a mono and an epi. So for all intents and purposes, I could think of my monos and epis living in orthogonal directions. They're not required to compose with each other. And instead, they're required to interact via the existence of these pullback squares that make both classes stable. So it's still about two classes of maps that don't necessarily interact in some kind of squares. And even our condition of the short exact sequences can be rephrased in terms of squares, because it turns out that a sequence like this is exact if and only if I form the commutative diagram that has A, B, and C. I'm going to complete it to a square by putting the zero object and the unique maps. And my sequence is short exact if and only if this square is bicartesian. So all of the conditions required here can be restated in terms of certain squares. So this was kind of the first observation that led people to think that you could have K-theoretical frameworks that didn't really need an underlying category and instead could deal with a double category. So now I will tell you about the first of the two frameworks that I want to talk about today for K-theory, involving double categories, I mean, and that's called CGW categories. So these are due to Campbell and Zakharevich. So they were the ones that noticed this story that I just told you and introduced these structures. And then myself and Brandon Shapiro strengthened the axioms to get them to behave a little bit better. So what are these categories trying to do? What's the purpose? So honestly, I was kind of sold from the start. I think it's very cool. Like, it seems like there's some double categories underlying all this story, so why wouldn't you try to do that and see what happens? But actually, the purpose was to try to introduce a structure that axiomatizes the very bare bones that you need to do K-theory. So axiomatize the essential features of these abelian categories that you needed for K-theory And importantly, something that we didn't mention at all beyond the existence of a zero was the underlying additive structure. So it turns out that you don't really need an additive framework, and that allows you to have tons of other examples. So notably, these are not going to be additive. All right, so how are we going to do this? Well, the first thing that we're going to try to do is answer the following question. How do I turn an abelian category into a double category? And we kind of went over this already. We said, okay, we can take the same object. Let's say my abelian category is called A. I'm going to construct a double category whose objects are the objects of A, whose horizontal morphisms are my monos. My vertical morphisms are going to be my epis. And now I need to kind of decide what I want for my squares. And since I do have an underlying category, I'm going to go with the obvious choice and just take commutative squares. And we'll see how far that takes us. Okay, so then in orange here on the side, I'm going to start to define our double categorical structures, but I want to keep in mind the motivating example of these abelian structures, just because these axioms can be a little bit abstract. So I'll start the definition. A CGW category is a double category. And now I'm going to denote by M its underlying horizontal category, because I want to think of these as being monos, and by E the underlying vertical category, because I want to think of these as being epis. Okay, so the first thing we want to do, and this is a little bit annoying, but it turns out that it simplifies everything that comes after, is it's going to be very much simpler if both of the directions in my double category are completely symmetric. And right now in my abelian example, they're completely dual. So the way to fix that, I'm just going to do something very formal. And I'm going to say my vertical maps are going to be the obs of epis. It's a little bit annoying, but now these are really symmetric. They're both going to be monic in both directions. And now I want to start to see, okay, this is kind of the structure, but what were the properties that I needed to do K-theory? So what were the properties that I'm supposed to be encoding? So first of all, it was important to me that I had monos and epis. So now if I continue my definition of CGW, I'm going to have an axiom that tells me that all maps in both M and E are monic, because I'm taking my epis opt, right? So then I was also using the fact that I have a zero object, but now I really only care about the relation to the zero object of my epis and my monos. And in my abelian category, I have that zero is initial among the monos and terminal among the epis. So now, since I'm flipping the epis, I'm simply going to ask for the existence of an initial object that acts as initial for both M and E. I don't really need it to be a zero object because that's not the behavior that I have if I only look at my monos and my epis. All right, so then it was also important for me to be able to do kernels and co-kernels. So if I have a mono, I should be able to take its co-kernel. But actually, I can do this functorially as well. So if I start with a commutative square and I take the co-kernel of both of the monos that I see in there, it turns out that I get an induced epi between those co-kernels. So I can do my co-kernel construction at the level of commutative squares. And that allows me to phrase it better in terms of the double category side of the story. So now I'm going to ask that there are functors So I'll have a functor co-cur. So what does this do? This is going to go from the category whose objects are my horizontal morphisms in the double category, and whose morphisms are the squares between them. And what is it going to produce? Well, I took a mono and I produce an epi, but now remember that I'm opping these for the vertical maps. So I'm going to produce vertical maps as the objects. And now if I look at the kind of squares that I get, they're all living in the underlying vertical category. So this goes to the category of just commuting squares between vertical maps. And of course, the dual notion of the kernel with the correct categories. Okay. But now I also have the fact that every mono and every epi determines a short exact sequence, and I somehow want to phrase this in double categorical terms. So we said a way to pass my short exact sequences into square language was to use bicartesian squares, but I don't want to say bicartesian because that's talking about a universal property in some underlying one category that I don't have anymore, right? So I need to find a way to encode bicartesian squares with the language of the stuff that I've already introduced. So what's special about bicartesian squares? Well, if I start with a commutative square here, A, B, C, D, I can take the kernels of the epis and the co-kernels of the monos. So of course, I get an induced map here that's mono, an induced map here that's an epi. And it turns out you can do the exercise in our modules that this induced map will be an iso if and only if this induced map will be an iso if and only if the square that we started with is bicartesian. So it's possible to characterize bicartesian squares completely in terms of the behavior of the induced map between the kernels and the co-kernels and those we have introduced, because that's just talking about something about a horizontal map and about a vertical map. So that's how this part of the structure is going to be encoded. So we're going to ask that whenever I have a square and I take its co-kernel in this direction, I get an induced map, or I take its kernel in this direction and I get an induced map. I'm going to ask that this is an iso if and only if this is an iso. So that's a property that I'm asking for my double categorical structure. And in this case, I'm going to say that the square is distinguished. And these distinguished squares, which in the original papers are denoted by a tiny square inside of the big square for some reason, are going to play the role of my special bicartesian squares. So now my fact that every mono determines a unique short exact sequence, I can phrase it in double categorical language by saying every horizontal map determines a unique distinguished square where I have my map over here. I have the 0 with the vertical map to A. And now if this is I want to have co-kernel of I participating in a distinguished square here. And this is playing the role, this over here is playing the role of my short exact sequence here. And everything that I've said in orange has been purely in terms of double category terms. So this is how you define these structures. And there's tons of additional axioms that you can choose, kind of optional if you wanted to have a slightly better behavior. For instance, there's the way to model having pushouts or stuff like this. But what can you do when you have these? So, okay, what can we do? with these CGW categories? Well, it turns out, first of all, that you can do K-theory. That was kind of my whole claim. So you can do both a Q construction and an S-dot construction. And this goes by like translating verbatim the usual pictures. Now you would write them in your double category language. So what do I mean by this? Before, for the Q construction, we said we have spans of an epi and a mono. So now I am flipping the epis. Now these are going to be spans of a vertical map followed by a horizontal map. Just formally take these spans. How would you compose? It turns out that some of these axioms in the interplay between taking kernel and co-kernel are going to allow you to always complete a piece like this to a unique distinguished square. And that's how you do the composite. Similarly, for the S-dot construction, before we had things like this. Now, all that we're going to say is the maps that you see in the horizontal direction in the picture have to be horizontal maps. The maps that you see in the vertical direction have to be vertical maps, but we're going to flip them because that's what we do. And we ask that all the squares that appear in the picture are distinguished. So it's kind of a silly game to play, actually. And it turns out that this gives you a spectrum. And in all the cases where you already had another K-theory machinery, like for the case of abelian categories, you're producing the correct spectrum. So they give you the same K-theory. But more importantly than like recovering examples that you already were able to do, you have new examples now. So more examples. And what I wanted to highlight were these new non-additive examples that you have. For instance, you can do sets. So this is not the most exciting of examples, but it's very illustrative. So how would you do sets in this double category language? You would take as your objects just sets, as your horizontal maps and vertical maps. I'm going to take inclusions of sets. And now I'm going to leave the squares blank for a second and try to see what happens with the structure, right? So this is how you would construct one of these things in practice. If you wanted to do K-theory of your own example, you need to figure out what all of this data is. So how would you do that? Well, you typically already come with an idea of who the maps should be. And then you start to play, okay, who am I really trying to split here? And that's going to give you the notion of the squares. So now for sets, I would have an inclusion of sets here. And if I take my initial object, which is of course going to be the empty set, and I take a vertical inclusion here, then whoever plays the role of my co-kernel, I'm supposed to have a co-kernel here that includes kind of naturally into B. So I need to, from an inclusion A into B, I need to construct some obvious other set that includes canonically into B. And what I can take is just the complement and the inclusion of the complement. So it turns out that if I do this, then this square is going to be bicartesian. So what's happening here is that the notion of co-kernels are to abelian categories as complements are to sets. That's kind of the slogan that this is telling you for the purposes of K-theory, of course. So now if you wanted to figure out the squares, the actual squares, not just the distinguished squares that give you these short exact sequences, you would say, okay, if I start with a square of inclusions of sets, then if I take the complement here and I take, let's say, okay, this should be a D, and I take the complement here, then this has to be something that induces an inclusion on the complements. So you can play around to figure out what this condition should be, and it turns out that this happens if and only if my square is a pullback. So my squares here are going to be Cartesian, not just commutative, because that's what's going to give me the correct kind of structure. And then distinguished squares are bicartesian. So this allows you to do K-theory of sets using this framework. It turns out that as all K-theorists would expect, the spectrum that you produce is the sphere spectrum. So it's a pretty cool one and also a completely incomputable one. But maybe more interestingly, you can use the same trick of getting these inclusions and these complement inclusions to do a lot of other examples that are also complementy in flavor. So in the same way, you can do K-theory of varieties. If you want smooth varieties, optional. By taking closed and open inclusions and just the complement of your variety in the same classes of squares. You can play the same game for any extensive category, where now your maps are going to be given by complement inclusions, by coproduct inclusions. So really, you get a ton of non-additive examples that have this complementary flavor that you couldn't really do before. Okay, so that's for these CGWs. These are the more complicated ones. But in the time that I have left, I want to talk about another framework based on squares that are aptly called squares categories. And what these are all about, so we said, okay, for these CGWs, the purpose was to axiomatize the abelian setting and recover some new non-additive examples. What was the reason for this other framework? Well, what this framework is trying to do is to accommodate examples where you have four-term relations. So what do I mean by this? Even though I'm using squares here, it's still kind of important that I have these three-term squares here, right? I mean, there's the initial thing, but it's not really giving us any valuable data. It's still kind of, there's a three-terminess underlying all this, because they're still coming from these short exact sequence analogs. But what if you really want to encode a full four-term relation? So that's why these came to be. And so what's a squares category? In stark contrast to the huge list of axioms that you needed for CGW, a squares category is a flat double category. And by flat, all I mean is that each square is uniquely determined by its boundary. So if I give you a boundary, it either contains a square or it doesn't. So squares are kind of a property now. It's a flat double category, which has an object 0, which is initial in the underlying horizontal category and in the underlying vertical category. So for each object A, I have a unique horizontal map from the 0, a unique vertical map from the 0, no other conditions, and this is it. So it's basically nothing. It's basically a flat double category. That's a squares category. It's like the complete opposite to the other thing that was super, super structured. So basically, I don't have much. So there's not that much to work with. However, if I scroll up to our Thomason construction over here, we said this is simply the horizontal nerve of a double category. So a priori, it didn't really matter that I had some weak equivalences, that I had some cofibrations, that I had some pushouts, whatever. Whenever you have a double category, you could do this. You could take the horizontal nerve and slap a loop space in front of it and produce a space. So that is literally how the K-theory of these things is defined. So K-theory, loops on horizontal nerve. And that's it. So what makes this legitimate, I suppose? Well, both legitimate and useful. There's this theorem that tells you if for every object A and B, you can find an object X that fits into squares. So I have the square with A and B, and I want to fit it in here. So this is a square. Or I have the square with B and A, and I want to fit X in here. So if I can always do this for any A and B, know that I'm trying to take like a co-product thing or like a direct sum thing. That's what's trying to happen here. So if this condition happens, then the K0 of this, by which I mean the pi 0 of this space that I just defined, is going to be described precisely as the free abelian group on the objects of my double category, modded out by the relation that for any square, A, B, C, D, I have that the class of A plus the class of D is equal to the class of B plus the class of C. So if I have this condition, then the connected components of my space are recovering these four-term relations. And this was used in a couple of papers kind of recently to do K-theory and encode K-zeros that we couldn't do before because they didn't quite fit into any of the formalisms that we had. So for instance, my favorite one is to encode manifolds up to cut and paste. So let me draw some manifold pictures. And I'm so happy that I can draw pictures in some of the work that I do. This is the first time that this ever happens. So suppose I'm working with manifolds with boundaries. I can construct a K-theory that tells me the following. Suppose I have the inclusion of this manifold into like a torus with a hole. So it's including in here, and that I can include it into the one where I filled the bit. Okay, so what happens if I take the push out of these manifolds? Well, I just get a torus. So I would like to have this is called cut and paste, because basically you take your manifold, you cut it, you open it up, and you paste it however you want. And this is studied in people who do manifolds. These are called SK groups, for the German for cut and paste. So you would like to have a way to encode this relation that the class of this one is the class of this one plus the class of this one minus the class of this one, because it's repeated, right? This is kind of an inclusion-exclusion relation happening here. So it turns out that this manifold example didn't fit into any of the previous frameworks. However, our squares categories are so unstructured that, like, sure, I can build a double category by putting these manifolds into it. And it satisfies this condition. So it turns out that the K0 of these precisely encodes this cut and paste relation. So this work, I'll just finish with a citation. This is work by Bugsema, Merling, Murray, Roby, and Semikina. Okay, so I'll just say the upshot. We have these structures based on double categories to do K-theory. When would you like to use them? Mostly when you are in a non-additive setting that doesn't fit into any of the other frameworks. If you have something that looks complementy, you would try to use the CGW framework. That's the hardest to prove because you have to check a bunch of axioms. However, it has very, very good foundational theorems about it. So it's the one that we understand the most. Of course, that's the cost benefit, right? It's a robust structure, so we can prove stuff about it, but it comes with a lot of data that you need to check. If you had a 4-term relationship that you wanted to encode, you would probably try to do the squares K-theory. That is the easiest one to construct by far, but then we don't really know much about it, and it's still in development to try to say things if we add some properties to it. And I will finish here. Thank you for your time.
Thank you very much. Sorry, thank you very much. We've got some time for questions now. Please feel free to pop them in the chat or raise your hands. And in the meantime, I'll ask a quick question. So you say that these squares categories are thin double categories. And in the CGW categories case, they're not thin, but there's not really any information in the two cells encode a property, right? They don't encode extra data. Is that?
Yeah, honestly, I don't know of any examples that wouldn't be thin. It's
Okay.
not a requirement, but it turns out that typically the way that you construct them. So honestly, even I'll go a step beyond this. Most of the times where you would use one of these frameworks, you do have an underlying one category.
Mhm.
The problem is that you have 2 classes of maps and they don't fit into any of the other frameworks because they either don't behave well with each other, or maybe they don't have a 0 object and they only have an initial object. Maybe you don't have all pushouts in your underlying category. So you would try to turn it into this framework that's really bare bones in a way. But all of the examples that I know even come from that. Yeah.
Okay, that's good to know. If anybody else has any questions, please raise your hand. If not, I might ask another one. Oh, no, sorry, no, Nathaniel Arker has put one in the chat. They say, if you have a double category for which you can apply several of those frameworks, is there a good way to compare the K-theories resulting from the different frameworks?
That's a great question. Yes. So okay, so here's the results that we do have. Whenever you have any of these homotopical structures that I was talking about before, whenever you have a Wallhausen category, you can always construct a squares category with it, and they give you the same K-theory. You don't necessarily have a way to construct a CGW category, just because you have cofibrations that behave well, but you don't have fibrations. So Wallhausen categories don't have the symmetry that you would expect. However, when you can construct a CGW, we prove that they give you the same spectrum as well. So yeah, basically, whenever you have a machinery, whenever you have an input that can be fit into a bunch of things, the things have been compared and they produce the same space.
Okay, thank you. And then we have time for another one. So Daniel, let me unmute you.
Can you hear me?
Barely.
Okay, yeah.
No,
Maru,
yes.
thanks for the excellent talk. This was very interesting. But so yeah, these square categories they're much more general than these Waldhausen categories. But in particular, they're not abelian. This is curious. So there are some categories which obviously are not abelian, but have notions of cofibrations like any module category, like spaces. Can you sort of go and now sort of do like K-theory of spaces like this? Does this use anything interesting or anything like that when you have sort of both? Because I mean, I really want to put sort of the horizontal should be the cofibration, but if I also have a notion of vibration, I want to put them in the vertical direction and see if that's something interesting, sort of this the square double category that you get. Can you say anything on this case when you
I actually don't know. So let's say that we have a model structure. I'm not sure. So what would you, the question is kind of, what would you want to do for squares? Because you would still try to have these cold fibers encoded there somewhere. However, I don't think it's the case at all that if you take a cold fibration and you take the cold fiber, that the cold fiber is a fibration.
Yeah.
Right? Like here, the cold fiber of a mono is an epi, but I don't think the cold fiber of a cold fibration is necessarily a fibration. Now, maybe you can replace it to be a fibration. So perhaps you will want to encode that replacement into this square or something like this. But I don't know how well behaved that would be, because then you need this to be a double category, right? So you need these squares to compose. So I guess you would need to be recording all of these choices so that it's functorial in a way. It seems kind of a hassle. I'm not sure it's doable.
If you dualize this construction and instead of talking about co-fiber sequences, you ask about fiber sequences, then there are many cases where your co-fibrations are monomorphisms, and those are stable under pullback rather than push up. Is that anything that makes sense here?
That I actually don't know. So there's a dual version of Wallhausen categories. So Wallhausen categories are pretty much categories with co-fibrations and weak equivalences and some nice properties. There's the dual notion of a category with fibrations and weak equivalences. And for some reason, we don't really do that in K-theory. Like mostly the examples come with a natural class of co-fibrations that we want to highlight. So I actually don't know what would happen if you just took the fibration approach and you additionally knew that that you have these like injections stable under pullback. I'm actually not sure.
Okay. Thanks. I'll talk to you later. Yeah.
Okay, thank you. So that we can get the next talk started on time, I'd like to thank Maru again for your talk. Thank you.